Hello, my name is Francis Ginger. Today we're going to be doing basic matrix operations. So some goals for today are to teach when matrix addition and subtraction is defined, to teach when matrix multiplication is defined, and to teach how matrices and these operations are useful in everyday life. So by the end of this lesson on basic matrix operations, you should be able to add and subtract matrices, you should be able to multiply matrices by scalars and by other matrices, and you should know what matrices, matrix elements, and matrix equations are. So before we get started, some just background information that you need to know. You must be able to do basic addition, subtraction, multiplication, and division. If you don't know those, I suggest you go watch a video on how to learn how to do those, and then come back and try to do this. But if you don't know those, you will certainly not be able to do this. To start off this lesson, we ask the question, what is a matrix? Well, a matrix is a rectangular array of numbers that are arranged into rows and columns, and it is a compact way of representing those numbers. The general form of matrices are open brackets, capital letter, closed brackets, and it is read as, in this case, that is matrix A. The capital letter just represents the matrix in question. It could be any letter A through Z, or well, now that we know what a matrix is, we want to know what the dimensions of the matrix are or how large it is. So a matrix's size can be written as x, small x, y, where x is the number of rows and y is the number of columns, and the dimensions are read as x by y, with that tiny x being read as by. So we know what a matrix is and we know how large it is, but what if we only want one number in that entire array of numbers? Well, that is called a matrix element. And a matrix element is a matrix entry that is described by its position in the matrix, and it is also referred to as a cell sometimes. The general form for a matrix entry is A subset xy, where x is the row and y is the column of the individual entry, and A, once again, is just a generic matrix used to represent the matrix in question. Just a real quick example, this right here is a basic matrix and it is titled A, and it is a 2 by 2 matrix, and we have numbers 2, 9, 7, and 4, and this represents matrix A. And so matrix A is a 2 by 2 matrix, and the first number represents the number of rows, 2, and the second number represents the number of columns, which is also 2. And so now we just have a simple matrix element. 8 to 1, well, you go down 1, 2 rows, and 1, okay, across 1 row, so 8 to 1 is 7. 8 to 1 does not equal 9, because you don't go across, then down, you go down, and then across. Now it is time to learn how to add or subtract matrices. To add or subtract matrices, you simply add or subtract corresponding entries. The addition and subtraction of matrices is transitive, so the order of the matrices does not matter. What does matter is that the matrices must be the same size. If they are not the same size, matrix addition and subtraction are undefined for that scenario. Alright, so super quickly I'm going to do some addition and subtraction examples using 3 matrices, 2 of which are going to be 2 by 2 and 1 of which is going to be a 3 by 2, and I'm going to time-lapse that now. And we are back. So the matrices I decided to use for my first one, I decided to have a 2 by 2 that was 1 1 was 12, 1 2 was 19, 2 1 was 7, 2 2 was 4. My second one, matrix B, was 3 8 and then 5 and minus 11. And my third one, matrix C, the 3 by 2, was 6 14 0 1 23 and negative 10. So for our first example, we had matrix A plus matrix B. Very simple, you just add corresponding terms. So 12 plus 3 is 15, 19 plus 8 is 27, 7 plus 5 is 12, 4 plus negative 11 is 9 is 7. And then for the next one we had B plus A, same exact thing. 3 and 12, 15, 8, 19, 27, 5 and 7, 12, negative 11 and 4, negative 7. So now, and then we decided to add matrix A to matrix C. Well, we can't do that since matrix A is a 2 by 2 matrix and matrix C is a 3 by 2 matrix. And so this one's missing spots to add to that, so matrix A plus matrix C is undefined. So then we did matrix C plus matrix B. Same scenario, we have a 3 by 2 matrix added to a 2 by 2 matrix. And since this one doesn't have enough slots, matrix C plus matrix B is defined as undefined. So now we have subtraction. We have matrix A minus matrix B. So very simple, basic subtraction. 12 minus 3, 9, 19 minus 8 is 11, 7 minus 5 is 2, 4 minus negative 11, so 4 plus 11 is 15. And then, to show that order doesn't matter, we have negative B plus A, which would be the same thing as A minus B, equals what? Well, negative B, so negative 3 plus 12, well that's 9. Well, negative 8 plus 19, well that's 11. Negative 5 plus 7, well that's 2. Negative 11, or positive 11 plus 4 is 15. So these two things are equivalent. Next I decided to have B minus 8 to show that even though order doesn't matter, it does matter if one minus the other is not the same as the other minus the same one. They're different. So we had what? 3 minus 12, well that's minus 9. 8 minus 19, that's minus 11. 5 minus 7 is minus 2. And then negative 11 minus 4 is negative 15. And that's different than the other two because you're taking this one minus this one, and you're not doing this one minus this one. And then finally we had matrix C minus matrix A, which 3 by 2 matrix minus a 2 by 2 matrix, we can't do that, so that answer is undefined. In those examples, I did two things that I have not yet explained. For one, I used matrix equations, and I also multiplied one matrix by a scalar. First off, what's a matrix equation? Well, a matrix equation is an equation where the variables are matrices. So instead of having an equation like x plus y equals z, instead we have a matrix equation that reads matrix A plus matrix B equals matrix C. And then to multiply a matrix by a scalar, you simply multiply all the entries in the matrix by a scalar. And the scalar is just a fancy term for a real number. And so in the examples, it was negative B plus A. Well, negative B is the same thing as negative 1 times matrix B, and that equals negative 1 times 3, 8, 5, negative 11, and then you just multiply negative 1 by all those entries individually, and you get negative B, negative matrix B, is equal to negative 3, negative 8, negative 5, and 11. So real quickly, I'm just going to do an example that uses a matrix equation and has scalars in it so you can see more accurately what it's like. So our example was 4 times matrix A plus 8 times matrix B equals 7 times matrix C. And for matrix A we had 15, 7, 11, 28, and matrix B equaled 9, 17, 23, and 5. And so, well, we just substitute our matrices in for our matrices there. So we have 4 times 15, 7, 11, 28 plus 8 times 9, 17, 23, and 5 equals 7 times the quantity of matrix C. Well, 4 times matrix A gets you 60, 28, 44, and 112. And then 8 times matrix B gets you 72, 136, 184, and 40 equals 7 matrix C. And then we just add these two together since we have two 2 by 2 matrices. And so we get 132, 164, 228, 152 equals 7 matrix C. And then over here we multiply 7 matrix C by the scalar of 1/7 to cancel out 7 and 1/7 they cancel out, they make 1. And then we multiply this matrix by 1/7 to get the answer what matrix C would be. And after you plug that into your calculator, matrix C, these are all approximate answers because they're all decimals. But you get 18.857, 23.429, 32.571, and 21.714. Moving on, now we're going to talk about multiplying matrices. For matrix multiplication to be possible, the number of rows in matrix number 2 must equal the number of columns in matrix 1. And if this is not the case, then matrix multiplication is undefined. But however, if this is the case, and matrix multiplication is possible, then the new matrix has dimensions of z by x. And this means that order matters. So where I get the term z by x is in a matrix xy, x by y, multiplied by matrix y by z, you will get a matrix that is z x by z, so that these two matter. So now that we have defined matrix multiplication, how do we actually perform it? Well, to multiply matrices, you take the dot product of matrix 1's rows by matrix 2's columns to get the entries in the resulting matrix. And the dot product is the first term in row 1 times the first term in column 1, and then plus the second term in row 1 plus the second term in column 2, or column 1, plus etc. Until all of your terms in row 1 have been exhausted and all your terms in column 1 have been exhausted. And then you move on to column 2. So you take row 1, the first entry in row 1 times the first entry in column 2, then the second entry in row 2 or 1 times the second entry in column 2 until all of your columns are done. And then you go down a row. So then you take row 2, first term in row 2 times the first term in column 1, second term in row 2, second term in column 1, etc. until all of your terms, until all of your columns have been used. Then you move over a column, and then you move over a column, and then you move down. And you do this until there are no more columns and rows left, so that you've taken the first row times the first column, the second column, this nth column, and then you take the second row times the first column, the second column, the nth column, and you take the nth row times the nth column, and then you have successfully multiplied your matrix. I am going to be showing an example of this with variables in the next moment. So here is our example. We have matrix A times matrix B equals matrix C. So matrix A is some random combination of numbers represented as A, B, C, D, and B is a random representation of numbers as E, F, G, H. They're both 2 by 2 matrices. Now the first thing I do is to make sure that A is matrix multiplication defined. So we have a 2 by 2 matrix times another 2 by 2 matrix. And we see that the columns on the second one is equal to the rows on the first one. So we know that matrix multiplication is defined. We also know that the resulting matrix, matrix C, is 2 rows by 2 columns. So matrix C is a 2 by 2 matrix. So to multiply, we take this first row times this first column. So we take A times E plus the next terms. So B times G. So our first entry in matrix C is AE plus BG, and that is one entry right there. Entry 2 is going to be the first row times the second column. So it's going to be AF plus BH, and that is the second entry. And now we move down a row, go back to column 1. So now we have CE plus DG as entry 3, and then we move over a row, and CF plus DH. Now we've exhausted all of our rows, and we've exhausted all of our columns. So this is our resulting matrix. It is a 2 by 2 matrix. And we can check that by saying, well, 2 by 2. We know that the 2 by 2, it has to be, like we said, have the amount of rows from the first matrix and the amount of columns from the second one. And 2 by 2 is what you get when you multiply a 2 by 2 matrix by a 2 by 2 matrix. So this is what it is. I'm going to be doing an example with a 1 by 1 matrix, a 1 by 3 matrix, and a 3 by 3 matrix, just to show you what will go on, and that's going to be time-lapsed again. So for our 1 by 1 matrix A, our number generator gave us the number 4. For B, our 1 by 3 matrix, we got the values of 56, 15, and 12. And our 3 by 3 matrix, matrix C, was 72, 68, 24, 59, 43, 13, 7, 1, 23. And I decided to do all of all the possible combinations of these. So A times B, A times C, B times A, C times A, B times C, and C times B. And A times B is defined since it is a 1 by 1 times a 1 by 3. The rows of the second equal the columns of the first. And so we get 4 times, or matrix A times matrix B, which is 4 times 56, 15, and 12. And in this case, the 1 by 1 matrix basically just acts like a scalar. So we have 4 times 56, which is 224. We have 4 times 15, which is 60. And we have 4 times 12, which is 8. And that is the matrix. B times A is a 1 by 3 times a 1 by 1, so matrix multiplication is not defined. A times C is a 1 by 1 times a 3 by 3. Matrix multiplication is therefore not defined. C times A, 3 by 3 by 1 times a 1 by 1. Matrix multiplication is not defined. B times C is defined because it is a 1 by 3 times a 3 by 3. I'll get to that later. And then C times B is a 3 by 3 times a 1 by 3, and so that is not defined. So B times C, well, that's this matrix right here, 56, 15 times 12, times this large orange matrix, 72, 68, 24, 59, 43, 13, 7, 1, and 23. And to do that, we take the first value, we take this entire row and we multiply it down. So we take this first value, 56, and we multiply it by 72, which is where our value comes in. We take 15 and we multiply it by 59, which is our second one. We take 12 and we multiply it by 7, which is our last one. We multiply the parentheses and then we add them all together to get us a value of 5001, and that is the first term right here, since I ran out of room to write all 3 of these large numbers. So our second one, denoted 2, is 56 times 68, then it's 15 times 43, and then 12 times 1. And if you plug that into a calculator and add them together, you get 4,465. And so finally, the last entry in the 1 by 3 matrix is going to be 56 times 24, 15 plus 15 times 13 plus 12 times 23. And that gives you a value of 1,815. And so the resulting matrix of B times C is a 1 by 3 matrix that has values 5,001, 4,465, and then 1,815 as the answer. Now that we know what matrices are and how to add and subtract them and to multiply them by whole numbers as well as other matrices, what can they be used for? Well, some real-world applications are that they're used in video games and like graphic design. To like character models are stored typically as matrices, and then the computer processing unit it runs a series of calculations and moves your character based on the input you do on a keyboard or a controller. And it's also good for like modeling, that you can like scroll around and you don't want to have your design completely just fall apart as you scroll around in your computer. And so that the computer will store your design's information as a series of numbers. And so when you rotate it, i.e. apply a transformation to it, it stays constant and will scale your visuals based on what you do to it. It is also used in scientific studies. It's great for storing large quantities of data fairly easily. So it's used in surveys and scientific studies and plotting points on graphs. And finally, one other use for it is it's used in search engines like Google. So if you say, if you type in 2 keywords like Bob Ross, you're going to get all of the results that include something of Bob and something of Ross, and sometimes most of them that have both in it. And yeah, there's all sorts of things matrices can be used for, since they're complex or compact storage for numbers, and this is just a few of them. So now that the lesson on basic matrix operations is over, what have we learned? Well, first off, we learned what a matrix was. We also learned how to add, subtract, multiply, and scale up matrices. We learned some real-world applications of matrices, and we learned that when adding matrices, you have to have the same size matrix, and that multiplying matrices are sometimes undefined and sometimes they aren't. Join us next time, as I discuss Gaussian elimination.